Dear students, under the lecture series on complex analysis, we are learning about continuity and differentiability. Now, here we have a problem which says that prove that the given function f of z equal to z, real part of z divided by mod z, if z is not equal to 0, and 0 if z is equal to 0 is continuous at z equal to 0, but not differentiable at z equal to 0. So we have to understand that we have to prove that the given function f of z is continuous at z equal to 0, but at the same time it is not differentiable. So we have to prove that it is not differentiable at z equal to 0. So we shall divide the proof of this problem into two parts. That is, the first one to check the continuity of the given function f of z. So let us do that first. So for a function f of z to be continuous at a point z naught, we have three conditions. That is, limit z tends to z naught of f of z should exist. So the existence of this limits is the first condition. The second condition is the function should exist at the point z naught. So f of z naught exists. So this is the second condition. And the third condition is the limit that we say that exist should be equal to f of z naught. So that is the third condition. So limit z tends to z naught of f of z should be equal to function at the point z naught. So if we prove all these three conditions, we are done with the proof that f of z is continuous at the point z equal to 0. So here z naught is 0. So that will be our first part. So let us first prove that the limit of the function exists as z tends to z naught. So now here in the given problem, z naught is given to be equal to 0. That is the point at which we have to prove the continuity of the function will be taken as z naught. So here the given point is z is equal to 0. So the value of z naught is equal to 0. So now we shall consider limit z tends to z naught. That is, what is z naught here? 0. So z tends to 0 f of z. So that is equal to limit z tends to 0 of, what is f of z given in the question? It is z and then multiplied with real part of z divided by modulus of z. We know that the function z, complex function, is taken as x plus iy. So from this, the real part of this z will be equal to x. And we know that modulus of z is equal to square root of x square plus y square. All this we have learnt as the basic concepts. So now we shall substitute each of them over here. So this will be further equal to, now since we have converted z as x and y, as z tends to 0, we know that x will tend to 0 and y will tend to 0. And z is x plus iy multiplied with real part of z is x divided by modulus of z is square root of x square plus y square. Now we shall check whether this limit exists. So now in order to check that, we have to choose a path along some curve. So let us choose a path along y equal to mx. So this will turn out to be, so this will be further equal to limit. Now since we have taken y to be equal to mx, we will have only limit x tends to 0 because y we are going to write in terms of x. So limit x tends to 0, x plus I, what is y? Mx multiplied with x divided by square root of x square plus y square is m square x square. And so this will be further equal to limit x tends to 0. So in the numerator x can be taken in common. So it becomes 1 plus im and it gets multiplied with this x and it becomes x square divided by, in the denominator x square is common and it is 1 plus m square. And further this will be equal to limit x tends to 0, 1 plus im multiplied with x square divided by this x square. When taken out of the square root, it becomes x square root of 1 plus m square. So that will be further equal to, we can cancel one of the x and we will have limit x tends to 0, x multiplied with 1 plus im divided by square root of 1 plus m square, and this will be equal to 0 as x tends to 0, because when we take here 0, this term completely becomes 0, and therefore the limit exists. Because it is equal to 0, we have a value for the limit, which implies that the limit exists, and the first condition of continuity is satisfied over here. So we see that limit z tends to z naught of f of z exists. Now we shall check out for the second condition. So the second condition is to check whether f of z naught exists. So what is f of z naught? F of z naught is equal to f of 0, because we know that the value of z naught is 0 in the given question. So what is f of 0? That is, what is the value of the function when x takes the z takes the value 0, we have to check. So when z takes the value 0, so f of 0 is given to be 0 only. So from this we can write this to be equal to 0. So since we are getting 0, it exists. So this implies f of z naught exists. So therefore, the first two conditions are done. The third condition is that we have to prove that limit which existed is equal to the value of f of z naught. And obviously we see that the limit that we have got is 0, and the value of f of z naught is also equal to 0, which implies that limit z tends to z naught of f of z is equal to f of z naught. So therefore this implies f of z is continuous at the point z is equal to 0. So therefore we have proved the first required part of the proof, that is, we have checked the continuity, and of course the given function is continuous at the point z equal to 0. The next is we have to prove that it is not differentiable at z equal to 0. Let us prove that. Now we shall check the differentiability of the given function. In order to check the differentiability, we have to check whether f dash of z naught exists or not. That is, what is f dash of z naught? It is limit z tends to z naught of f of z minus f of z naught divided by z minus z naught. So if this exists, then we say that the given function is differentiable at the point z not given, that is z is equal to 0 is the point given here. So let us check the existence. Now here we have z naught to be equal to 0. So therefore f dash of 0, so at the place of z naught we will substitute 0. Limit z tends to z naught, so z tends to 0, f of z minus f of z naught is f of 0 divided by z minus 0. So now we shall substitute. So this is equal to limit z tends to 0. What is f of z? It's given in the question. That is z real part of z divided by modulus of z. So z real part of z divided by modulus of z, and then minus f of 0. What is f of 0? We saw that it is equal to 0 only. So since f of 0 is 0, minus 0, it's going to be the same, divided by z minus 0, which is z. So this we can also write it as limit z tends to 0, z real part of z divided by modulus of z multiplied with 1 by z, because z by 1, which can be written as 1 by z. So this z and this z gets cancelled, and it's equal to limit z tends to 0, real part of z divided by modulus of z, which is further equal to limit z tends to 0. What is real part of z? It is x. So we can write this as x tends to 0 and y tends to 0. So x divided by modulus of z is square root of x square plus y square. Now we shall check whether this limit exists or not, for which we have to choose a path. So let us choose the path along y equal to mx. So along y equal to mx, our f dash of 0 will be equal to. So this is equal to, we shall substitute y equal to mx over here. So we will have only limit for x then, since we are changing y in terms of x. So limit x tends to 0, x divided by square root of x square plus m square x square, because y is equal to mx, y square we have to write, so m square x square. So that is equal to limit x tends to 0, x divided by, now square root of x square is in common, and then 1 plus m square. So further this can be written as limit x tends to 0, x divided by, when this x square comes out of the square root, it will become x square root of 1 plus m square. And so further this x and x gets cancelled, and we have limit x tends to 0 of 1 by square root of 1 plus m square. We see that the limit depends on the value of m. So as the value of m changes, the limit will also change. The reason is, for example, we shall take when m is equal to 1. What will happen when you substitute m as 1? It will, the limit will be equal to 1 by square root of 2. Similarly, when m is equal to 2, so when m is equal to 2, so 2 square is 4, 4 plus 1 is 5, and the limit becomes 1 by square root of 5. So we see that the limit keeps on changing. So as the value of m changes, the limits will also change, which implies that this function, that is f dash of 0, is not unique, which implies this is not, the limit is not unique, and therefore the limit does not exist, which implies that the function f dash of 0 does not exist. So the existence of this is the required condition for differentiability. But since this does not exist, f of z is not differentiable at the point z equal to 0. So hence we have proved that f of z is not differentiable at z equal to 0. So this is also a very good example for to show that a function which is continuous is not necessarily differentiable, because we know that all differentiable functions are continuous, but it's not necessary that all continuous function has to be differentiable. So this is one of the best example for that. Kindly follow the next video lecture for a similar problem of this kind. In fact, that is a very important problem for the examination point of view. Thank you.